Okay, so this is where we left off, right? The system so far. We have, ability to add data to the system. Our two registers, our little ALU, which is a very simple ALU. It's basically an adder where we can make it also a subtractor. Our address register and RAM, so we can store information, we can add stuff, and we can output information, which is nice. I mean, obviously before down here, we were outputting information, but kind of like the spirit of what these two things are is a little different. This was more of like a, let's observe what's on the bus, right? Because this is always showing what's currently on the bus, and it's just there for, I don't know, we can see how it's changing, right? You look at this and you're like, what number is that? Go! And you're like, oh, I don't know. But output register, well, that's like, what is the computer actually like intending to be outputting? So that's what the output register is doing. So we've come quite a ways. So right now, okay, we can clearly see, and obviously in that last image, let me go back real quick. Somehow, back? How do I do this? What's the hotkey for back these days? Whatever. All the control signals down here. Sometimes you'll hear me say like control logic. Sometimes you'll hear me say control signals, same idea, okay? I think there is like a nuanced difference, but it's not too important for us right now. So the control signals, okay? By turning these on and off, hitting the clock, things will happen. And it's great and all that we have the ability to like manipulate these signals manually, pulse the clock, and things happen. We move data around, we do addition, subtraction, we move data around again, we output data. Great. But we know that when we're using a computer like the computers we have, like obviously we write instructions and then the system goes and executes these instructions automatically. Right? We say, go add these two numbers. You didn't have to go say add the numbers by going like, okay, clock. Right? You didn't do that. That's ridiculous. So we clearly need a way to work towards being able to give instructions to this system to have it go do things automatically, where the system has the ability to like manipulate itself. And that's a big key thing. And that's kind of what we talked about near the end of the last semester. Our last lecture was like with the power to like manipulate, like self-reference gives you the ability to like manipulate yourself, but it also creates like kind of like those little conundrums of paradoxes. I don't know if you'd call that a problem, but with that, like with the, like, it's like this necessity. It's this really like interesting thing to me where in order to have this self-reference to be able to do things like really interesting and solve complex problems and like create these complex systems where self-reference, we have self-reference. Like you and I have we have self-reference as well. This is a very important feature of these sophisticated complex systems, which is a really good thing. But with that, we necessarily introduce the problem of creating things like the paradoxes. Maybe calling the paradoxes a problem isn't really fair, I don't know, but like, oh, sophisticated complex systems, good. But as soon as we get that, we also introduce paradoxes. So that's kind of interesting. I always found that a really interesting phenomenon. And I want to make sure it's clear that I'm not talking about like computers. I'm talking about like within our universe, in the set of rules that exists within our universe, like we introduce the self-reference, but with this amazing power, we introduce this like evil beast, these paradoxes that has to come with it. Like they exist. It's interesting. Anyways, back to computers. Okay, so we need we need a way to write instructions for our computer. And we need a way to keep track of the instructions. We need to, like, we want the instructions to execute one at a time. And so there's this idea of a program counter that we're going to need. And the program counter is a very simple module on the computer. What it does is it knows, let me hit pause. Eventually, let me hit pause again. RAM is going to be filled with data and instructions, right? I've shown you examples where the contents of RAM was data, right? Like I showed you like where I hit run and I went and put like 15 and 4, right? And then I loaded 15 into the register, 4 into the register, right? That's the data. But we also want to be able to like put instructions in RAM. We want to be able to store like, okay, go add these two numbers together. I want to put that into RAM. And the computer can go and be like, oh, the first instruction is go add these two numbers or something. So I need a way to put instructions in RAM. And each instruction is going to be stored sequentially. That's how, that kind of makes sense. Run line 0, then line 1, then line 2, and then line 3, and so on. Okay? Or in this case, it would be address 0, 1, 2, and so on. So the program counter is going to be a module in the computer where we can say the value in this module, it's going to be a register, the value there is the address of the next instruction to be run. Not, you might want to call the next, it's kind of like an edge case. We'll discuss that in a moment. But it's always going to store the value of the next instruction to be run. And then after we get that next instruction, and we say, okay, we need to, let's say we start at 0. Go run, the program counter contains the value 0, because that's the next instruction to be run, the first one. We go load it up. What should the program counter do? Program counter, what should it do? What do you think? It should increment, it should count, right? So what comes after 0? It should just turn into a 1. Perfect. So now it's got, well, the computer's going and doing its thing to execute instruction 0. It's going to be like, well, I should also become like 1, because that's where the next instruction is going to be. So this is the idea of what we want the program counter to be. But, like, we also want the ability, like, look, if we want to get the value out of the program counter to be like, okay, well, what's the value of what's the address of the next instruction? 0. I need to get information from the program counter. Turns out, and we're going to see why as we go, but it turns out it's going to be very important that we have the ability to put information into the program counter. So if the system is like, my next instruction is like address 7, right? And then the system itself goes, actually, your next instruction should be address 0. We have the ability to change, the system has the ability to update where its next instruction actually is. We'll see why shortly, but here's a spoiler, like loops, right? You want to repeat the same chunk of code? A loop. Now, has anyone ever heard of this idea called like a goto? So in some of these older programming languages, instead of like having like a formal loop, you could be like goto line, yada yada, right? And then there's like this long history of like why this is a stupid idea, why you should never use gotos. And people have used these ideas of gotos, why like the continue keyword should never be used, even though continue or having breaks, having breaks or having like early return. People have used this argument in that case, but that's actually a bad argument, so don't fall into that. But long story short, people like never use gotos. Well, turns out we don't really have that option when it comes to like how we're going to be programming our system. We don't have the sophistication to do anything beyond effectively a goto, but I'm getting ahead of ourselves, okay? Long story short, program counter needs to store this instruction of the next, or the value of the next instruction, the address value of the next instruction. All right, so as of now, only data was stored in RAM. However, RAM will eventually store instructions in addition to data, although instructions are technically data. And really, at the end of the day, the information in RAM, it's even worse than that. The information in RAM is just low voltages and high voltages to be interpreted however one wants, but more on that later. These instructions are going to be retrieved from RAM one at a time, so the system can execute that instruction. Now, you may have also noticed, though, that like when we added those two numbers together, there was several steps involved, right? That took several clock cycles. We didn't just say, okay, go add. We had to like put data in the registers, output from the ALU, like there were a couple of steps involved, but okay. The program counter is a component that keeps track of the memory address of the next instruction to to be performed. It effectively keeps track of like the line of the program to be run next. Although line, like the address, the memory address. But if we think of the memory addresses as like lines of code. Any questions before we get going? Okay, it has several important functions. It keeps track of the memory address of the next instruction to be run, incrementing memory run. It increments the memory address stored. Okay, so we know where it is. And it also has the ability to be like, okay, well, if I just ran line 0, I should now be 1, should be the next value to run. But we have to be careful. Like I just said, we saw that some instructions actually take several clock cycles to perform. Right? I really mean like what we just saw. Like here was adding 15 and 4, right? I inputted to A. Okay, so that might not be the best example. Whatever. Here I'm just loading value from like the data inline. But the point is, like, there's I had 3 clock pulses to add 2 numbers together and output it, right? Now, we actually could have a conversation and be like, well, actually, how many what should an instruction be? Add 2 numbers? Should adding also include outputting? Or should adding and then outputting be 2 instructions? This is a question we have to determine for ourselves later. But the point is, like, this basic, like adding 2 numbers together and outputting the result is some unit of work that we achieved that we may or may not want to be an instruction to tell the computer, go add these numbers and output it. Should that be 1 instruction, 2 instructions? I don't know, but the point is, either way, there's 1, 2, 3 clock pulses, right? The program counter, we can't have it increment every clock pulse. Because if this was like, okay, go add 2 numbers and output the result, is 1 instruction, we want the program counter to increment by 1. But if it incremented every clock cycle, it would increment by 3. So we have to be careful. We can't have the program counter increment every clock pulse. We need to have very deliberate timing when we increment our program counter. Is that clear? All right. Instructions often take several clock cycles to complete. Thus, there needs to be a way to control when the program counter increments. We're going to do this very intentionally. And we need to output its current value. And we also need to be able to set a value to a specific memory address. This is going to be very important for things like loops and conditions. A very important feature of the system. This would be another example of the system has the ability to like manipulate itself. All right, so storing and incrementing values. Okay, well, here's a very simple design. What do we have? Well, I've got my clock, whatever. I've got a program counter E, program counter enable. I've got a register. And I've got, what is this? So you look at this configuration, what do we got here? Well, I've got a program counter, okay, sorry, pardon me. I've got a register, so it's going to store a value. I can get data from here and, you know. But what is this going to do? Well, this will take whatever value is in the register, add 1 to it plus a 0 carry, and it outputs its value back into the register. With this design, every clock pulse, okay, let's assume it starts at 0. So after 1 clock pulse, well, okay, remember, this is the only thing that's sequential here. When I say sequential, to remind you, what I mean is it's the only thing in here that effectively, like what it means is it needs a clock pulse, okay? Remember the flip-flops, the things, how the registers worked? We needed clock pulses to make the data like go in and latch. An adder was not sequential. The adder can like always work. It doesn't need a clock pulse in order to work. So this stores 0. 0's in here. This is outputting 1. If I were to hit run on this, before any clock pulse happens, this stores 0. This is storing a 1. Now, if program counter enable is low, I can clock pulse all I want. This is never going to change because this never updates. That means this never changes. That means 0 plus 1 is always still 1. But as soon as I enable that, every clock pulse, this is going to go, okay, 0, 1, 2, 3, 4, 5, 6, 7, right? It's a very simple design. Now, obviously, this is not our program counter, but I have a feeling something like this is going to be used very, easily for our needs. All right, so storing a value can be achieved with a register, obviously, and incrementing a value can be achieved with an adder, where we always add 1 and a 0 carry to some input. With the above configuration, the adder is always adding 1 to the stored value in the register, being output by Q. However, even though the value at the register D's input is always Q plus 1, it only updates when enabled, when the program counter is high, like I just said. This design provides control over when we increment. So what do we achieve here? We achieve the ability to store information. To store information, but we can't set it. But let's assuming it starts at 0. We have the ability to hold on to the program counter value. We have the ability to increment. And we have the ability to control when it really increments. So there's a lot there. We've got a lot. Now we need a way to control when the program counter outputs. Okay, we've got data stored in there, but I want to retrieve data from the program counter. So that's not too bad. Now, where do we want to output from? We got to be careful. You might be tempted to put the output over here, but no, we don't want to output here because that's not the value in the this is the value in the program counter. This is the value in the program counter plus 1. If I want the value in the program counter, I need this, right? So this is what I want to observe. This is what I want to get. But in order to actually control the output, we'll simply use a driver, or in your case, a transistor, right? Where when this is off, this will be Z, nothing's being output. When this is on, whatever value's in here gets output. Cool? Cool. So now we've added the ability to control when we output. To control the output, use a driver like the previous designs. Note that the counter's Q is the output. The output of the adder is for updating the state of the counter. Yes. Okay. So now, when do we want to control inputs? Well, we've added a level of complexity here, but it's not too bad. What do we still have from before? We have our register, our adder. It loops back in, but we've got a multiplexer. More on that in a second. And we have the ability to control output. But what's new here? Well, what's new is I've got the ability to input data. I've kind of rejigged this layout here, where I have program counter input and program counter enable. I'll give you 30 seconds to look at this and try to make it make sense to yourself. So what's going on? Well, okay, we've got an OR gate for the enable. We have two possible inputs to the register that's controlled with this program counter in. So what's going on? Well, okay, look. Let's focus first on program counter in. If program counter in is 0, this OR gate as a 0 here. So its state, the register's state really will depend on program counter enable. If program counter in is 0. And if it's 0, which of these two lines are we going to get? Well, we're going to get the top line, which is the +1 value. So if this is a 0, and this is a 0, this will become 1, assuming it's enabled, and there's a clock pulse. If this is a 1, then I don't care if program counter is enabled. But if this is a 1, we take from the data input line. And that gets mapped to the register. Then, because this is 1, data in this is 1, because this is an OR gate, and if that's 1, you know, it's 1. That gets enabled. And then on the clock pulse, whatever stored in here gets put in here. And then regardless if this is a 0 or a 1, for simplicity, assume this is a 0. Just when this is 1, this is enabled, and it just feeds in from there, and it counts. So that's the design. Not overly complex. It's not, I wouldn't say it's trivial, that's for sure, but that's the design. I always kind of find it fun where, like, we want some function, you know, when we're writing code, right? We're all experienced writing code. When you're writing code, what are the functionality do I want? You write the code to make that functionality, right? Here, it's like, well, what functionality do I want? Well, what's the physical arrangement of things, of the components to get what I want? Like, it's like we're programming, but in a very different way. But we are. Any questions about this design? Cool. So, okay, in addition to incrementing, the program counter must be able to store specific input data. Therefore, the counter's register must be able to store one of two potential values, the value from the adder containing the incremented value, or the data from elsewhere. A multiplexer can be used to control which signal we want. A program counter in controls the multiplexer, but also when we enable it. Yeah. And either program counter I or PCE are high, the program counter will be enabled. In this particular configuration, what would happen if they're both high? It's not a trick question. Let me rephrase the question. Does it really make sense to have them both high at the same time? Not really, right? You could make maybe someone could continuously try to make an argument, and then you'd be like, okay, fine, fair. But really, it doesn't make a lot of sense to me. Because program counter enable is more about, like, okay, increment. Where input is read from the input. If they're both high, this is enabled. But if they're both high, that means this is high, which means we're reading from here, meaning we ignore whatever this is anyways. So if they're both high, it means read the input. Program counter enable is effectively kind of like useless in that particular case. You might say, well, should we change the design such that you can't ever have them? Be my guest to try to figure that out, but I don't think you're going to get any value out of it. Just the system, that would be like, it's not even like it's an invalid state. Like, it's valid in the sense that, well, what would that mean? Well, we want to enable the program counter and input. When we input, we necessarily are enabling the program counter to, like, you know, enable the register. So it's not so much that it's invalid, but it's also kind of like this state supersedes this state, kind of. Yeah. All right. So if either the program counter I or enable or high, the program counter's register must be enabled. And then how would we actually add this to the data bus, to our system? Remember, this is kind of like our general design for, like, imagine we have the data bus. It's isolated from the rest of the ESAP system right now, but this is the idea. How would we add it? Well, that's how. It's the same design that we just saw, except the fact that the data in is from here, but what's going on here? Well, one sec. And then the data out from here, okay, it's coming here, but what's going on here? Well, okay, do I explain it down here? Okay, so you might remember that RAM has 16 memory addresses, right? So how many bits do I need to uniquely identify 16 unique values? 4. The program counter is used to keep track of a memory address. I only need 4 bits. The data bus is 8 bits. I only need 4. So I want my program counter to only store 4 bits. But the data bus has 8. I can't put 8 bits into 4, so what do? Well, here I just cheese it and just do a splitter and ignore the most significant 4 bits. I keep track of the least significant 4 bits. If you're saying, why is the least significant 4 not the most significant 4? Well, because by the design of how we added it to the, maybe do I have it open? Yes. Because by this design here, we kept it was the least significant 4 that are used to index RAM, right? So that's what we're keeping. You'll notice that this is like this, and this one is that way. Just be aware it's different. It doesn't matter. It was just a setting. It was for design purposes. If I put it down below, it would make it go wider. I didn't like it being wider. I know, I'm being picky, but whatever. My pickiness made this so much harder to design. Because I'd design it and be like, I need to move where this is at this point, which means I need to go back and change everything from weeks. It's the whole thing. All right, so that's why we're keeping the bottom 4. But then this also poses a similar problem on the output from the register, putting back onto the data bus, in that I have 4 bits, but I'm trying to put 4 bits onto 8. I can't do that, so how do I do that? Well, I'll use a merger with the bottom 4 bits plus 0, 0, 0, 0. Just merge that, and then there we go, 8-bit driver. Happy? Sad? Yeah? You might say, why not put this merger back on this side? I don't know. I feel like the driver is like this really is right here part of the data bus. The driver to me is like the boundary of like the program counter not. So I figure like put all the crap there. And it just makes more sense to me. Did it really matter? No. But it makes more sense like that to me. So any questions about this general idea? In fact, this is an example of one of the designs that I decided to change later, and I had to go back and change the system, like all of the images and everything. It was such a pain in the butt because I decided, well, give me a moment, you'll see. All right, so due to the ESAP system's design, we only need 4 bits to index RAM. Therefore, we need some mechanism to interface between the 2 different bit lengths, the 8-bit length versus the 4-bit length. So we use a splitter and a merger. Now, it turns out there is a counter component in digital. So that whole design can be abstracted into that little guy right there. And that's what I mean, right? I originally had this in the ESAP design, but I decided to replace it with like an abstraction because that's kind of the spirit of this whole course, right? Is just abstract, 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 right? Yeah, yeah. So there we go. That is what we're going to use in our design. There's 2 different, if I remember correctly, there's 2, maybe there's more, but there's at least 2 different counter components in digital. One is one with presets. Basically, you can like load in values, which is what we want, right? Okay. This component includes several inputs not required for the ESAP system's design, though. The clear input, which resets the counter to 0, is not needed. The direction input, which controls the counter direction, does not need to be manipulated. We always want the counter to count up. We don't need it to count backwards. So some of these things here we don't need. We just kind of like we just kind of like tie them to values that they just need to be set to, right? Like, oh, direction, you can change that. I need it to always be 0 or 1. Just tie it to a constant 0 and you just set it and forget it. It's nice. Physically, you would say you would tie it down or tie it up to like, if it needs to be 1, you tie it to like a high voltage. If you need it to be a 0, you tie it to a low voltage. That's all. Or pull it up, I can't remember because it's pull-up resistor. I might be getting my wording wrong, but you get the idea. So here's how I would design it, right? There we go. To be clear, this clear thing here, there's a clear input. That could be handy a lot of times to like reset the system or something, but our system doesn't have like a reset. We just turned it off and on. So we don't need to like physically build a reset configuration. If you've ever been to my office, you'll see a breadboard in the back behind me. That's a computer based on a similar design, but it's physically built on a breadboard. And on that one, because I don't have the ability to like reset things, I had to build like a circuit to clear everything. Because like I've been saying several times before, in reality, with all these components, if you're like, well, just turn the power off to the system and put the power back on. But when you do that, all the values and all the registers with all the transistors are just set to arbitrary values. They don't start at 0. But I want them to start at 0, so I need something to be like, okay, 0, and that's how that works. Where with this, I don't need to do that. I just turn it on, everything's 0. It's an idealized scenario, which is good. All right, so what do we got? Well, it's the exact same design. I just took out all those different components, put in the counter. Enable output. That is, Ian. Oh, no, that's enable out. So there's the output overflow. We ignore the overflow, doesn't matter. That would be like a carry out, right? If it was an adder, carry out. Enable, clock, direction, and clear are set to 0. We never want to clear. We never want to change the direction. These values are set and forget. In is the in, and then LD, that's load. Load, program counter in, yeah. And then output right there, PC out. Cool. It's the exact same idea. We just abstracted all those components into this little box right here. Nice, right? So how would we add this to the system? Well, there, just like that. I just threw it in right there. I just copy and pasted it all in. And that's what's nice about this design, right? Is like I can take this, I can go here, what I literally did when I built this is I took my design and I opened up this file, I selected, I copied, I pasted, and just connected the dots. And that was it, simple as that. There we go, there we go. I added it to the design, I added the control signals because the program counter has 3 different control signals. I moved them down here. And like I've mentioned before, the order, you might say, why are they over there? Well, it's so the lines look nice, right? With the amount of time I spent making these lines look nice and how much going back and reorganizing things and changing a lot, you better appreciate this, okay? That's all I'm saying. So as with the previous module, the control signals are moved to the bottom. The order of the control signals from left to right is not important, although it is if you want a nice design. The current order was selected for visual clarity. Yeah, okay. Again, as with the previous modules, the placement of the program counter is not important. What is important is how it's connected, but I put it there so it aligns with this overview image that we were using. So it's the exact same design. We just added the program counter, and the program counter was like up here, right? And before talking about the program counter, if you would have input and output, you may not have thought, why do we need input? Well, again, to enable things like looping and whatnot. All right, well. Okay, so in the previous topic, we added 15 and 4 together, right? So in order to do that, I had to manipulate the data inlines to specify memory addresses, right? And then I'd specify a memory address, then I'd say, okay, output from RAM to the A register. And then I'd go reconfigure the lines to say memory address 1. output the value from memory address 1 to the B register, right? Right, you remember how I had to go and manipulate at the top. I did data input for the memory values. You might also remember that I said in last class that, like, isn't it neat that because I put all the data I needed into the system before I hit run, I didn't need to load data in when it was running. But we kind of did because the address values needed to be loaded in. Like we had to manipulate it. But, you know, the address values, they're data, but they aren't. Do you know what I mean? Right? Like, what was my program doing? What was my computer doing? It was adding 15 and 4. What was the data? 15 and 4. The memory addresses are data, but they really are data that is not important for the what we're doing. It's important for the how we're doing it. In the sense that, like, well, I need the memory address to get data out of RAM and to put into the address register. But if you knew nothing of the design, and I was able to like hit run on this program and you watch the output, you wouldn't think about the memory addresses. I might not be explaining this well, but the point I'm making is the address values, they're data, but they're like an ancillary data. I don't know how else to describe it. It's like data that corresponds to how the system is running. It's data that was needed in addition to the control logic to do its thing. But what was I doing? I was adding 15 and 4. I needed to know the data was at memory address 0, memory address 1, right? But that was important for like specifying it and, you know, the control logic. That was important for like the steps that I was executing, not the what I was executing, right? Maybe it's not clear, but I'll try to make it clear with the next example. So what we're going to do, like before, I'm going to preload data into RAM. But remember how like before when I preloaded data into RAM, I hit run and then I went to RAM and then I manipulated the values, right? You remember how I did that? Well, this time what I'm going to do is I'm going to actually preload data into RAM with a hex file instead. We've already loaded data into hex files like we did, or hex files into digital like we did with the output register, but we can do it for RAM as well. So here's what I'm going to do. I'm going to create a hex file. First, actually, let me open up here, program counter, okay. There. Okay, cool. Actually, here, let me make sure. Here. Program. Yeah, okay, that's what I did. All right. Before we do that, let's make sure, let's play with the actual program counter for a second to convince ourselves it does what we want it to do. Okay, run. Okay, we can see. There's a 1 on, okay, this line here, Q out, it starts with a 0. 1, because 0 plus 1, yeah. But this is a 0, and this, well, I guess this is a 0 on it because there's a 0 on the data bus. Let's change that to be Z. There. Okay, so if none of these signals are there, I can spam clock and nothing changes. Perfect, right? So far, so good. Program counter out. We now see a 0 on the data bus, right? I can spam, nothing changes. I can enable now, and that it should now start counting, right? Perfect. Perfect. But notice it'll only count to 15. 15, 0, because it's only a 4-bit register with a 4-bit counter here. Right? Yeah? Happy, sad? So now, let's turn that off, and let's put in a value. Well, actually, for fun, let's do this. There. Let's load this value into the program counter. Well, what is this value? Well, it's F5, which, okay, it's F5. But what value will actually be loaded to the program counter if I were to do this? 5. Why? Well, because the top 4 bits are entirely ignored. So let's do program counter in. What does that do? Well, okay, it goes in through this, so the output of the OR is still 1, because it's an OR, and this is 1. But the multiplexer's signal is now not the one from the adder, but from the data bus. So whatever value is here, F5, which if we go over here, is 5. This is 5. What's in here? It's still 0, but once I clock pulse, oh, ooh, we left clock high. Ooh, did it go on the up or down? Okay, so it goes on the up, boom, there, now it should be 5. There, cool. Remember that the data latches only latched on the high clock pulse. No, if it was already high and it went low, nothing changes, it has to go high. So there we go, cool. So now we read the data in. Let's turn that off. Ooh, it incremented though. Ooh, that was fun. Oh no, it didn't. That's still a 6. This is still a 5. Okay, cool. Turn these off. Okay, output, what should we see? Well, we should see the 5. And now it counts again. Yeah, program counter. If we were to go and load up this thing here, it should work the exact same way, right? Enable, oh, nope. Output counts, should count to 15. There we go, cool. And then turn that off, turn that off. And let's put some value. There, input. Turn these back to Z. Yeah, perfect. We see 8. And then enable. There we go. Perfect. It works the exact same way we want it to. Happy. Perfect. And isn't it nicer to just see a component where we go like, okay, it's a counter. Neat. All right, so back to here. Okay, so what I want to do is perfect. There. Why do I have 2 additional zeros? Well, we'll find out. If I don't, okay. This is a hex file, right? I have 15, 4, 0, 0. Now, if I were to load this into RAM, RAM has 16 memory addresses, but there's only 4 values here. So even though I have zeros specified here, digital is going to go like, okay, but yeah, that's right. What? Is that right? 16, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Okay, there. Like digital would fill those other RAM addresses with 0. No data is the same as 0, okay? It's nothing. But for our needs, we'll go back to here. Okay. This first line here is required again. It's not my fault. It's not digital's fault. It's just the conventions and the rules around this type of file, a hex file. It's just got some data. I'm hard coding it here. If we go to digital, so you might remember here with like the lookup table, you would go like, okay, what's the data, edit, and you can see like file load. Well, we want to do the same idea with RAM, but unfortunately, RAM, we can't do that. But there's something here called program memory. So I can't specify what data to load into RAM right in here, but what I have to do is go to like view, edit, circuit specific settings, advanced, and yeah, here. Preload program memory at startup. Because this is a different type of thing. The lookup data, lookup tables, it's different than like, well, what's the program? Now, the program that we're loading into RAM, it's just data, but it's the program, okay? And what program? Well, I specify there, its path is, there, its path is right here. So I specified the one, okay? Okay, so when I hit run, and I right click on this, that data is actually already in there, followed by a bunch of zeros. Because again, there was only 4, there was an F, a 4, a 0, a 0, and you're like, well, where's the next 12 zeros coming from? Well, again, digital's like, okay, I just pad it with zeros. Okay. So with this, we now have data in RAM. But what I don't want to do is I really hate toggling those things. It's a pain in the butt. My data's in here, and the data that I want first is at address 0, but the program counter starts at 0. The data I want next is at address 1, but I can increment the program counter. So I think I can actually do the exact same computation. I can do the exact same computation of adding 15 and 4 together without having to specify memory addresses up here anymore. I should be able to do it by just saying, okay, give me the value from the program counter, increment the program counter. Something like that. I think we can do that. But we don't have time for it today. But that's what we'll start off next time. Do we have any questions? Today's Thursday, so tomorrow's Friday. We'll do it tomorrow. Oh, it'll be a great conclusion to the week. All right. Cool. I'll see y'all later.